Now we will generalize the gradient descent algorithm to the case of regularization. Here is the optimization objective for the regularized linear regression, which has been already showed before. The first part is the usual objective for the linear regression, this one. And now we have the additional regularization theorem. Lambda is the regularization parameter, and theta are, all of those theta are the parameters we want to find in order to minimize the cost function j of theta. Previously, we were using gradient descent for the original cost function, the one without the regularization theorem, and we had the following algorithm. This part shows the regular linear regression without regularization for parameter theta 0. In general, for theta j, where j equals 0, 1, 2, up through n, we will repeatedly update the parameter theta j, this one. It's important to remember why the term theta 0 is analyzed in an independent way of the others. We should remember that for the regularized linear regression, we penalized just the parameters theta 1, theta 2, and so on, to theta n. But not theta 0. So when we modify this algorithm for regularized linear regression, we are going to treat theta 0 different from the rest theta sub n. Concretely, if we want to take this algorithm and modify it to use the regularized objective, all we need to do is to take this term theta j and modify it as follows. So we will take this term, the theta n, and add lambda, this one, and add lambda over m times theta j. And if you can look at this new term, the one which has the regularization term, you can then see a mathematical relationship. This one. These terms corresponds to the partial derivative with respect to j of theta, using the new definition of j of theta with the regularization theorem. This term up of the bottom, that is also the partial derivative respect of theta 0 of j of theta. So this one. So if we group all the terms together that depend on theta j, we can show that this update can be written equivalently as follows. And all we did was to add theta j here, so theta j times 1, this one. And this term is right lambda, this one, and this one, which also depends on theta j, so there is also an alpha here, so you end up with alpha lambda over m multiplied into theta j, this one. And this term here, 1 minus alpha times lambda m, is an interesting term. It has an interesting effect. So this one, 1 minus alpha times lambda over m, will be always less than 1. This term 1 minus alpha times lambda over m is going to be a number that is usually a little bit less than 1, because alpha times lambda over m is going to be positive, and usually if your learning rate is small and if m is large, this is usually small. So this term here will be a number that is usually a little bit less than 1. For example, it's a number like 0.99. we are going to say that theta j gets replaced by theta j times this one. Theta j will be replaced for 0.99 theta j, and more formally this makes the square norm of theta j a little bit smaller, this one. So and then after that the second term here, this one, that's actually exactly the same as the original gradient descent update that we had before we added the regularization optimization. So this gradient descent, hopefully this update makes sense. When we are using a regularized linear regression, and what we are doing is on every iteration we are multiplying theta j by a number that's a little bit less than 1, so it's shrinking the parameter a little bit, and then we are performing a similar update as before. Of course, that's just the intuition behind what this particular update is doing. Mathematically, what it's doing is it's exactly gradient descent on the cost function j of theta that we defined on the previous slides that uses the regularization theorem. So this is the explanation of how implement regularized linear regression. Using this, we can avoid overfitting even if we have lots of features in a repeatedly small training set. And this should let you get linear regression to work much better for many problems.